Hello, everyone. My name is Minhaj, and I'm here to talk about one of our worst stories at LinkedIn. This covers how we went around debugging an issue that caused downtime to search. So let's get started. Galean is the library that powers search at LinkedIn. It's an internal library built on top of Lucy, which is pretty popular as it's the base for Elasticsearch as well. Anyone interested in learning more about a search stack can take a look at the blog post called Did You Mean Galean on LinkedIn blogs. The focus during this talk will be on one of the applications in the search stack called the searcher. Yes, I know it's a very generic naming, but that's exactly what this application does. It hosts the search index and runs queries on those indexes. So we have two indexes called the base index and middle index. The middle index gets updated with the current stream of changes and the base index stays constant. Like most other applications in our organization, we use cgroups to limit CPU and memory. This helps us co-host multiple applications. This is how it looks from a host point of view. We have a host, we have multiple containers in a host, and each container will host a production application. In container one, we have the searcher. In container two, we might have another application or another instance of the searcher itself, and so on and so forth. Let's go through a few concepts. The first is container. I'm sure that this is a buzzword along with Kubernetes, Docker, and everything. But going through it, in simple words, a container is essentially something that we put stuff in. In this case, the stuff is an application's code as well as everything that the code needs to run properly. Then we have control groups or C groups. This is essentially a kernel feature that limits, accounts for and isolates CPU, memory, and other resources of one or more processes. This helps us co-host multiple applications on the same host while ensuring that they don't use more resources than allocated to them. This is one of the building blocks of containers in Linux, along with namespaces. Then we have mlog call. This is a system call that logs part or all of the calling processes virtual address space into RAM, preventing that memory from being swapped page to the swap area. This helps us keep the entire searcher and all its indexes always in memory. Since the index is always in memory, a query can traverse through it pretty fast. Our latencies are kept in check this way. Then we have the killer or OM killer. I'm sure most of you are very familiar with this one, might have helped or might have destroyed applications. So strong opinions there. It's a process that the Linux kernel employs when the system is critically low on memory. The killer has to select the best process according to it to kill, and it does so based on an score that it calculates. Let's not go into detail on that. The killer is also invoked when cgroup memory limits are breached, but on a subset of applications under that cgroup. Then it's RSS or resident set size, which is a portion of memory occupied by a process that is held in the main memory or RAM. Now let's go to the issue we had. So we receive an alert, and yes, that's going to be a bad day. Then we see that we have multiple instances of our searchers being down. The day just turned worse. Receiving an alert is bad. Receiving an alert for a critical issue is even worse. So we log in and try to get everything up to speed. And since the applications are down, the first thing we have to do is restart it. So we run commands to restart, and at the same time take a look at what's wrong. But apparently the restarts don't go through. It looks like the host itself isn't responding. Now, that's not an easy problem to solve. because if the hosts aren't responding, we have to reboot them through the console. While we can do it, running it on a huge number of hosts isn't very scalable with the abstractions that we have. So we have to pull in other teams to directly access the console and get the host rebooted. And we get that done. Then the host is rebooted and we restart the application. And it starts up all fine, but not for long. The host starts going down again and we are stuck in that loop. So while somebody takes care of ensuring that the hosts are consistently being restarted and the application is up, others start debugging. And this is what we figure out. The hosts were low on memory, as shown in the host available memory graph. They have high disk read times. And one very interesting thing, there were no logs or any metrics generated on the host once it was unreachable. By no logs of any kind, it means no application logs, no system logs, nothing, no war log messages, nothing at all. And the gap here where there is like nothing on the graph is where the host went unreachable. Looking at the metrics, we also figured out that there's a lot of swapping going on. So the cause is that the host was running out of memory. But since there was no logs or such, it was very hard to figure out which application was abusing us and using the memory. So we did dig through, we couldn't find the real culprit hogging system memory. But then we had to figure out a way. So we looked at our application itself. In this case, it was an application hosted on a single host. We only had like a single container on that host, and the application used the entire host. So we took a look at our application and figured out ways to cut down on memory, like reducing the heap and optimizing our indexes. And we did that. And just to add another level of safety, we reduced the C group memory limit for the application as well. So as to ensure that we don't even reach higher and we just kill off the killer gets invoked, even when the application tries to use a little bit more memory. So this helped us to solve the issue, but like mentioned earlier, we couldn't find out the real culprit. The host has a bunch of applications that's run on it for the deployment stack, monitoring host health, and a lot of things like that to help optimum functioning. And it could be any of those. But anyway, once we reduced our memory, we didn't run into this issue again. So everything was good. But not for long. The issue happened again. But this time it was more interesting because we found out something that was new. So a searcher requested a huge chunk of memory this time. It didn't happen last time because we looked at the graphs and there was nothing of this sort. So you can see it here that the application memory usage in bytes graph, there is a huge spike. The working of the searcher doesn't require anything of this sort unless it is loading the indexes in memory. And this was not at that stage. So pretty interesting. So we dug into what's wrong and we figured out that there was a sidecar application to the searcher that requested this amount of memory. It was a bug in the code and this shouldn't have happened. And that was fixed. But it still shouldn't have broken the host. And we had to dig into that as well. So the previous time when we debugged, we didn't suspect Linux C group memory enforcement. We assumed that C groups will enforce our application's memory and it wouldn't cause any issues. But this time, since we had the issue 2 times, we had some doubts on it. So we thought, why not try it? So here we go. We tried to validate the issue by writing a C program and simulating it. We wrote one and we tried three methods. The first is allocating memory greater than the C group limit. The second one is mapping files and mlock all on the C program greater with the usage greater than the C group memory limit. The third one was running alongside the searcher and allocating more memory after the searcher starts up. And in all three cases, the killer invoked correctly. So we really couldn't replicate the issue, and we might have assumed something wrong. So we thought we'll dig more into C groups. And we started looking at the memory usage pattern on C groups. So here is this application C group memory usage in bytes graph. And if you can see, we have this point over here marked in red at 51 GB, and that's where the host went unreachable. So generally, the memory usage is a sum of RSS, page cache, and swap. But since our application cannot be swapped, we don't account for it here. But now we want to check whether everything adds up. So we looked at the RSS usage graph of application C group and the application C group page cache usage. Yep. And looking at the same time, it does match up. It shows 51 GB as well. So nothing wrong there. So we thought we'll take a different approach and look at it from the application's point of view. Now, we looked at the application metrics and figured out the base index and middle index sizes. We went and verified that on the host as well. And we also looked at the RSS value. And adding the index sizes, we got a value of 44 GB and the RSS value was 19. So adding that, we got 63 GB. So the application says that it's using 63 GB of memory, whereas C groups tells us that it's using like 51 GB. So somebody is reporting wrong here. And it's most probably C groups because we did validate these things from the application's point of view with the files and RSS. And that should be right. So what exactly is wrong? The actual page cache usage is 44 GB, but the one reported by the C group is only 31 GB. So we had to take a deeper look at that. Just some context on the hierarchy of our C groups. We have a root C group at the host level, which has two children. One is the system C group, which hosts applications for the deployment stack, for the host level metrics, for shipping of logs, and so on. And then we have the application parent C group, which is the parent C group for the application C group that hosts the production applications. And both the system C group and the application parent C group are unbounded C groups. What that means is that we don't put any limits on them. They can grow how much ever they want. But the application C group is in that way. We do put limits on them, and we expect them to kill off the application or throttle them based on what is set if it exceeds the resource usage. Now let's compare the page cache with the parent C group. The parent C group, and this is where the issue happens, and this is the application C group. And we see there's a huge dip in the application C group page cache usage. And this isn't supposed to happen because we essentially have that much big of an index, and this is definitely not expected. So we looked into why that dip happened. And it's caused by a restart. Now, we weren't really sure how a restart could really cause that. So we started looking at how restarts or deploys work in our stack. So first it stops the application, then it deletes the application C group, creates the application C group again, and starts it. Of course, this is for restarts, and deploys do have other steps where it pulls in the artifacts and stuff. Now let's look at how memory accounting works in C groups. For RSS is pretty simple. It's the sum of RSS of all the processes under that C group. For page cache, it's very interesting. For anything that didn't already exist in memory, it is very straightforward. If the application inside is going to create that part of page cache, it gets accounted to that C group. But it definitely gets complicated when shared page caches are involved. Shared pages are accounted for on a first touch basis. What this means is that any page that was created by a process inside a C group is accounted to that C group. But if the page already existed in memory, then the accounting gets complicated. In this case, the page will eventually get accounted to the C group after it keeps accessing that page aggressively. So let's take a look at how that works. So we have the C group 1 with an application inside it, and it creates a new page or multiple pages for 1 GB file in RAM. And that C group gets accounted for it, and it says that its page cache is accounting to 1 GB. Now a new C group is created, and it has an application running inside it, and it also accesses the entire 1 GB file. But the page cache accounted to it is 0 GB because it essentially doesn't own that file, and it's only accessing it. And the C group 1 is still the one that shows 1 GB of memory. Now, assume that C group 1 is dead and the application inside it is also gone. Even now, the page cache accounted to C group 2 is still 0, or it could be any value, but it's not the entire file, because for that to happen, C group 2 has to keep aggressively accessing the file. Until it does that, page cache doesn't get accounted to it. So once it keeps accessing the file, it gets accounted each page and slowly grows, and it accounts for the entire thing. And that's how it works. So let's look at how we validated these findings. If we take a look at this graph, it's for an application that was already showing the wrong amount of page cache. It was showing 19 GB. So we thought, let's try out something that validates our findings. So we went and stopped the application, and the page cache dipped, and we went and destroyed the C group. And we did a drop cache. Then we created the C group and started the application. So once it started, we can see this huge spike, and it started accounting for the entire memory very well. This verified that the issue was because a new application C group did not charge pages to itself, even if the application inside it is the only one using it. So let's see what exactly happened in our case. So we have our new index deployed. Which means that everything is completely new. All the files required for the page cache is new. And at this time, the application C group reports correct amount of memory, and everything is good. So, and slowly the application grows in size, and the indexes also grow in size. And we reach the C group limit. So whom killer is invoked, and the application is killed. But we do have an automation that runs and restarts applications. And it's a pretty dumb one. It just figures out what is down and goes and runs a restart. It definitely helps us because for various reasons our application can go down, and if the automation restarts it, it might potentially save us from an issue. But in this case, application C group memory started to be reported wrong. The new C group that comes up does not account for the indexes that's already there in memory. So, like we mentioned earlier, we already had the previous indexes in memory, and when this restarts happen, there's nothing to load back into memory since like things already there. So it just uses them. But at that point in time, since it's shared cache accounting, the C group doesn't really account for it. So once it does load everything, the application and the indexes still keep growing. Now we reach again a point where the C group limit is reached. But this time, the killer is not invoked by the application C group. Why? Because like we said earlier, it isn't accounting for the right amount of memory. So from its point of view, it's not using at all. Like it's not even at its limits. So why should I invoke the killer? And it keeps growing and the host gets low on memory. At this point in time, Linux itself tries to save itself. Linux tries to swap out applications so that it can free up some memory, but unfortunately, a searcher uses mlock all, so cannot be swapped. So other critical applications start getting swapped, and the host goes unreachable at that point, and there's nothing much to be done. And we have to reboot it. So that's what we figured out. And what did we do to fix the issue? First, we set up proper monitoring. This we used to monitor the application C group usage, but as we figured out earlier, that doesn't always equate to the right thing. So this time we moved towards using the application metrics for index size and RSS, and put up a threshold of a certain person based on the limits we set on the C group. This helps us catch an issue way earlier in terms of an index growth. So we figure out that something is going to break much earlier, and we have avenues where we can prevent it from happening. This helped us in case of situations where the index kept growing. But we still had the second issue, right? Where a sudden increase in memory usage, in terms of that, this wouldn't really help, because if a sudden increase happens and our host dies, like monitoring is not going to help because the host dies anyway. So we put up another mitigation as well. So we put a limit on the memory of the parent C group. So as we saw earlier, the parent C group is unbounded in our case, but it shows the correct amount of memory used. So we put up limits on it, and so that killer will be invoked when the parent is reaching its limit. This isn't exactly a perfect solution, because when the killer is invoked, it will run on all the applications under that parent C group. And this can cause a non-offending application to be killed, because again, how killer decides its score might not always pick the application which is using more amount of memory. It's definitely a big factor, but not always the case. But considering that the host itself will go down if we don't take action, and both the applications are going to suffer, we thought we can live with it. So what did we learn? First point, memory accounting in C groups and how page cache accounting is pretty complicated. When using C groups with applications that are heavy on page cache usage, always be careful not to depend on the C group metrics for memory reporting. They might not tell you the whole story. So it definitely helps for us to have metrics or logs on the actual application usage based on the files you use. Then we have mlock all. While this is core to the search architecture and ensures that our entire application stays in memory, so that we can have very good uh, latencies, it can also cause other issues. When under a memory crunch, our application wouldn't get swapped out, or even parts of it which are totally not used at that point wouldn't get swapped out. It can lead to other critical applications being swapped out and make the host unreachable. In case we didn't have mlock call, uh, in a situation where we have a memory crunch, the worst that can happen is parts of the search application gets swapped out, and yeah, we might see latency degradation, but not really bad, right? It might be just a tail because we do have most of the application still in memory. But anyway, when using mlock call, please be careful. The next one is never assume anything. In our first issue, we assume that cgroups are perfect and they would ensure that our application never stepped out of line. But that wasn't the case. And since we assumed that, we ran into the issue again and took some more downtime. So again, never assume anything and go through all avenues and challenge all assumptions. That's all, folks. Thank you for listening to me. I know it has been a long talk, and I hope I can answer all the questions on Slack. Anything more, we can always ping me on LinkedIn. Here's my ID. Thank you very much.